Let us continue our discussion on applications of differential scanning calorimetry in thermal unfolding of proteins and protein-solvent interactions. We have taken some examples of Hennig-White lysozyme. Whatever protein we take, the conformational stability of a protein is decided by the solvent environment also. And one way you can alter the conformational stability of a protein is by changing the pH. What happens when you change the pH? When you change the pH, when you increase the pH or decrease the pH tremendously, it will affect the conformation of the protein. If you lower the pH to a large extent, then many amino acid residues will have positive charges protonated, and excess positive charge will lead to repulsion and lead to the denaturation of the protein. And similar thing may happen at the other extreme of pH. So definitely pH may affect or will affect the thermal unfolding of protein, or that means it will affect the conformational stability of protein. Let us take a look at the slide. What is the effect of pH on thermal stability of a protein? I am showing here two differential scanning calorimetric profiles. One is for the protein RNase, this one on the left hand panel, and the other is for ubiquitin, this is on the right hand panel. And you can clearly see that when pH is changed from 1.8 to 5.5 or higher, there is a continuous increase in the thermal stability of the protein. Every protein will have its optimum activity under certain conditions, at a certain combination of pH, temperature, etc. And similarly, if we look at the transitions for ubiquitin, when you change the temperature from 2 to 4, we see a consistent increase in the thermal stability. And actually, if you see in both the panels, the increase in thermal stability is also associated with the area under the curve. In other words, the increase in thermal stability is also leading to an increase in the calorimetric enthalpy of unfolding. Obviously, if the conformational stability of the protein is strengthened, the calorimetric enthalpy will also be more, because the process will become more endothermic. You will require more heat to overcome those additional interactions. What else we can derive from this? We will discuss it a bit later. But let us see from the differential scanning calorimetric profile, what are the various thermodynamic parameters we can get more than those what we get at the transition temperature. Let us look at this question, which is Hennig-White lysozyme unfolds at 55 degrees centigrade at pH 2. The experimentally observed calorimetric enthalpy is 400 kilojoules per mole, and the heat capacity of the protein increases by 10 kilojoules per Kelvin per mole at the transition temperature. Calculate the values of delta G naught, delta H naught and delta S naught associated with the unfolding of the protein at 40 degrees centigrade. Comment on the values of these thermodynamic parameters. In the question, we have been given information at 55 degrees centigrade and we have been asked to calculate the thermodynamic parameters at 40 degrees centigrade. So obviously, since the temperature is changing 55 to 40, therefore it immediately reminds us that what is that thermodynamic parameter which connects a thermodynamic property from one temperature to another temperature, and that is heat capacity. Therefore, we will definitely need the value of delta Cp, the value of change in heat capacity, to calculate the required thermodynamic parameters. And that information is given. The given information, we look at this slide, T half is given 55 degrees centigrade, that is the temperature where transition is half complete, which is 328.15 Kelvin. Calorimetric enthalpy is given as 400 kilojoules per mole and delta Cp is given as 10 kilojoules per Kelvin per mole. Let us keep this data in mind and look at the differential scanning calorimetric profile. Let us take a look at this figure. We are given the information on T half, we are given the value of calorimetric enthalpy, and we are given the value of delta Cp. Now let us do some derivation. The process under consideration is native state going to denatured state. And for this, I can write equilibrium constant as concentration of denatured state divided by the concentration of native state. I am assuming the activities to be same as concentration. In other words, I am assuming that the solution is very dilute. Now at a temperature where half of the reaction is over, K will be equal to, if half of the reaction is over, that means both the concentrations are same. Once again, T half is the temperature where half of the transition is done. That means the concentration of denatured state and concentration of native state when half the reaction has taken place is 1. So therefore, delta G naught is equal to minus R T half log K will be equal to minus R T half log 1, and this is 0. So we must keep in mind that when the transition is two state means either native state is populated or denatured state is significantly populated and there are no intermediate states. And when the reaction is half complete, K is equal to 1, that means at the transition temperature, the standard reaction Gibbs energy, that change is 0, but only for two-state process. And if I now use this expression, delta G naught is equal to delta H naught minus T delta S naught, and since this is 0, I can write delta S naught at T half will be equal to delta H naught at T half divided by T half. This equation I am rewriting because delta G naught is 0, therefore delta S naught at T half is delta H naught at T half divided by T half. Okay. With these, now I can write temperature dependence. Delta H naught at any general temperature will be equal to delta H naught at T half plus delta Cp into T minus T half. This is Kirchhoff's law. That is, if I know the enthalpy of unfolding at transition temperature, if T half I am calling as transition temperature, and then since I know delta Cp, I can calculate delta H at any other temperature. Then let us recall delta S naught at any temperature will be equal to delta S naught at T half plus delta Cp log T by T half. This equation we have discussed many times, that entropy at any temperature is entropy at a reference temperature plus Cp log T by T reference temperature, and I am introducing just deltas in that equation. I can further write this as delta S naught at a general temperature T. Instead of delta S naught T half, as I just derived, delta S naught at T half is equal to delta H naught at T half divided by T half plus delta Cp log T by T half. And this equation allows me to calculate entropy change at a given temperature from the knowledge of enthalpy of transition at transition temperature and the changes in delta Cp. Now you see, I have variation of enthalpy with temperature, I have an expression of variation of entropy with temperature, and now I can calculate delta G naught, because delta G naught will be equal to delta H naught minus T delta S naught. So I will substitute these two equations and get the value of delta G naught. That is, let us now do it on a next sheet. So delta G naught at any temperature T will be equal to delta H naught at that temperature minus T delta S naught at that temperature. Now I will substitute for delta H and delta S. So delta G naught at any temperature will be equal to delta H naught, that will be delta H naught at T half plus delta Cp into T minus T half, this is delta H naught, minus T times delta S naught. I will write for delta S naught. Delta S naught was delta H naught at T half divided by T half plus delta Cp log T by T half. Once I solve this, I get delta G naught at any temperature is equal to delta H naught at T half into 1 minus T by T half. Plus then I have delta Cp, and inside I have T minus T half, T minus T half minus T into log T by T half. Delta H naught into 1 minus T by T half plus delta Cp, T minus T half will come here, and then minus T log T by T half will come from this. So I have an expression for temperature dependence of standard reaction Gibbs energy. Now let us go to the slide. What I discussed was, for this expression we just derived or discussed that K will be equal to 1, and then delta G naught, which is minus RT half log K, delta G naught is 0. So for such a reaction which is two state, we can immediately say that at the temperature where transition is half complete, delta G naught is 0. And then we discussed how to get delta S naught and how to get delta H naught, delta S naught at any temperature, and eventually we came up with this expression delta G naught at any temperature in terms of delta H naught and delta Cp. Now you see these three equations, this equation, and this equation will give you a temperature dependence of enthalpy, entropy change and free energy change. And these three equations are very important when you talk about folding unfolding transitions in proteins. That means if you know the data associated with the transition of the protein at a given temperature, at a certain temperature, let us say transition temperature, you can draw delta G naught versus temperature, or delta H naught versus temperature, or delta S naught versus temperature profile for a long range of temperature, and discuss the conformational stability of the protein as a function of temperature without doing the experiments at that temperature. Now coming back to the question which was being asked to us, with the given information, because that's all we needed, the transition temperature, we needed calorimetric enthalpy, and we needed the change in heat capacity. When you substitute this data in those three derived equations, we get the enthalpy of unfolding at 40 degrees centigrade as 250 kilojoules per mole, entropy of unfolding at 40 degrees centigrade as 0.75 kilojoules per Kelvin per mole, and delta G naught at 40 degrees centigrade as plus 15.68 kilojoules per mole. A comment can be made over here. Delta G naught at 40 degrees centigrade is coming out to be positive. It is plus 15.68 kilojoules per mole. A positive change in Gibbs energy means the reaction is not spontaneous. That means at 40 degrees centigrade the protein will not unfold, and that is in line with the given information that hen egg white lysozyme unfolds at 55 degrees centigrade. That means if the temperature is below 55 degrees centigrade, the reaction will not be, unfolding reaction will not be spontaneous. And that is what you see here is that delta G naught is positive at 40 degrees centigrade. In fact, if we look at this figure is drawn for the thermal unfolding of wild type, that is the solid lines are for wild type and the dashed lines are for R96H mutant of T4 lysozyme at pH 2 and 3. This delta G naught versus temperature curve you see has been generated from minus 20 degrees Celsius to 60 degrees Celsius by using this equation. Delta G naught is equal to delta H naught, actually read this as T half, delta G naught at T is equal to delta H naught at T half into 1 minus T by T half plus delta Cp and the remaining terms as we discussed earlier. So, by using this expression, the complete delta G naught versus temperature curves have been drawn as a function of temperature from minus 20 degrees Celsius to 60 degrees Celsius. And this one line up and the shaded area is actually representing the standard deviations in delta G naught when you incorporate the standard deviations of delta H naught, T half and delta Cp. According to this equation or in general based upon our previous discussion, the value of delta G naught should be 0 at transition temperature for a two-state transition. And you see, you draw a line at 0. Wherever this line crosses the delta G naught curve, that should be the transition temperature. So, at pH 2 for the mutant the transition temperature is this. For the wild type T4 lysozyme at pH 2 transition temperature is this. At pH 3 for the mutant transition temperature is this, and for the wild type at pH 3 the transition temperature is this. At pH 2, sometimes one may see two transition temperature and these two transition temperatures respectively corresponding to, this is the thermal unfolding and this is corresponding to cold denaturation, because denaturation can be carried about or brought about by heat as well as by reducing the temperature. So, in this way we can not only generate the free energy versus temperature curve, we can also generate the enthalpy and entropy versus temperature curve and draw a lot of conclusions from such plots. Now, let us discuss some more features from the differential scanning calorimetric output. Let us consider this equilibrium, n going towards d, where n I am writing for the native state and d I am writing for the denatured state. Now, if you increase the concentration of the protein, will it affect the transition temperature? If we look at this stoichiometry of the reaction, it is n going to d, 1 mole of native state producing 1 mole of denatured state. According to Le-Chatelier principle, if you increase the concentration of the protein to begin with, concentration of protein increasing means you are increasing the concentration of the native state. It should not affect the transition temperature at all, because it is not going to affect the equilibrium composition. Now, suppose if my process is N2 going to 2D, and now if I increase the concentration of the protein, once again increasing the concentration of protein means we are increasing the concentration of N2. According to Le Chatelier principle, the equilibrium should be shifted in favor of N2. An increase in concentration, that means equilibrium is in favor of N2. That means when you thermally unfold, the extent of oligomerization decreases during the denaturation because the reaction is towards denatured state. So, if an increase in concentration of the protein leads to an increase in the transition temperature, that means the extent of oligomerization is decreasing. Now, if I consider 2n going to D2. Now, what happens if you increase the concentration? If you increase the concentration, now the shift is, the Le Chatelier principle says that this should be favored. That means the equilibrium will be shifted towards D2. So, in that case, increasing the temperature will lead to decrease, in that case increasing the concentration of the protein will lead to decrease in the transition temperature. That means the extent of oligomerization is then increasing during the transition. So, this is what is commented now here. If the value of T half depends on temperature, then some conclusions can be drawn. For example, the value of T half may depend upon the concentration of the protein. If T half does not change with temperature, there is no association or dissociation of protein molecules during transition. If T half increases with increase in protein concentration, extent of oligomerization decreases during the transition. That is what I was trying to explain over here, that if you increase the concentration of the protein, the equilibrium is more towards N2. That means the transition temperature will increase with increase in concentration. But what is the net result? That the extent of oligomerization is decreasing during the transition. And conversely, if T half decreases with increase in protein concentration, the extent of oligomerization increases during the transition. In addition to commenting upon the extent of oligomerization increasing or decreasing with increase in or decrease in concentration of the protein, let us see what else we can get when we change the pH. We just discussed in the beginning of this lecture that the pH may affect the conformational stability of a protein. And when you increase the pH, and that is associated with the change in transition temperature and calorimetric enthalpy, that data can be used to calculate the extent of protonation of the protein when it undergoes denaturation. For further details, one can refer to this Journal of Molecular Biology, the reference which is listed over here. So, therefore, if the transition temperature either increases or decreases with change in pH, we should be able to calculate another property, another quantity, that is how many protons are either being accepted or how many proteins are being lost when this folding unfolding transition takes place. In other words, the extent of protonation or deprotonation of the protein when it undergoes denaturation or folding as a function of pH. If we have the data, that property can be calculated. So, in this lecture we discussed further applications of differential scanning calorimetry and treatment of the data which we obtain at transition temperature, that is how the data obtained at transition temperature can help us in calculating the thermodynamic properties over an extended range of temperature. And if we can know these thermodynamic properties over an extended range of temperature, then we can talk about the behavior of the biological macromolecules in that extended range of temperature. We will further take more examples on how this differential scanning calorimetry gives more information on protein solvent interactions and protein ligand binding, and these things we will discuss in further lectures. Thank you very much.